right. Good morning, everybody. Bon dia. We are Thomas Steiner, that's me, and
I'm Thomas Nattestadt, just to make it confusing.
There's too many Thomases, and we have another Thomas on the WebAssembly team in Google. So he goes by Thomas, I go by Tom, and we have this other Thomas who just, we need a name for him, but here we are. So today we want to talk about WebAssembly at Google, and we want to start with one big disclaimer. Google is a big company, so it's not two guys in a dorm room anymore. That's a long time ago. Last time we looked, it was like 100,000 employees. That's a lot. And despite the title, WebAssembly at Google, we can't really give you the full details at Google, because some things are just not public. There's cool things happening behind the curtains. But also, because Google is such a big company, there might be some team somewhere that does something with Wasm, and we just don't know about it. But yeah, we tried real hard to really give you the full details of who is doing what at Google. Google products need to run on many platforms. So obviously, there's the web with all the different browsers. There's Chrome OS. There's iOS, Android, Mac OS, Windows. So a lot of native, desktop, mobile, whatever operating systems. And we need to, in some cases, support products on all of them. So you can imagine that's a lot of work to make sure that feature parity happens. So for example, Google Slides, our slide software that we use to create these slides, there's an iPad app, there's an Android app, there's an iOS app. You can use it on the web, obviously. So that's just a lot of platforms that we need support for just one particular product. WebAssembly at Google happens at many different areas, or in different areas. And first, I want to dive into WebAssembly standardization a little bit. So Google contributes to WebAssembly's standardization. We are part of the that's a hard word to say on a Friday morning, W3C working group and the community group for WebAssembly, and we're championing a lot of proposals. So there's different stages, so you can see there's finished, phase 4, phase 3, memory 64 is a random chosen phase 3 example. We have extended name section in phase 2, so there's a lot of things going on. We will share the slides later, so there's a bunch of links, so you can just follow the links once you have the deck, and it's going to be easier. So there's just a lot of things going on, and most of them, I don't even know what they do, so there's a lot of really super in-depth things happening that are important for people who do certain things, but maybe not others. So there's a lot of work going on there. Right, so how does standardization work typically at Google? So typically, we start with someone who has an idea. So they have a proposal, they write a spec draft, and then two things happen almost in parallel. The V8 team at Google, our JavaScript and WebAssembly engine folks, they start and implement this prototype of the spec draft. At the same time, there's typically a product that needs this feature. So you can see in the concrete case, I've put the icon of Google Sheets. And Google Sheets was collaborating with the standards folks when WebAssembly garbage collection was being developed. And of course, both will have feedback. So the implementation in the product will have feedback. The implementation in the Wasm engine will have feedback. And of course, there's external feedback. So this is not happening at Google alone, obviously. There's also external feedback from people who are also involved in the standardization. So it's a back and forth. It's a circle. And eventually, we will then have a shipped standard. So that's a classic example. At Google, we also have a lot of Wasm infrastructure, as I want to call it. And first, I want to dive into two of them, Emscripten and Binarian. Emscripten, I guess most of you have at least heard of it, if not even used it. It allows you to compile from C, C++, LLVM to WebAssembly. And then we have Binarian, which is a set of tools that is used by Emscripten and many other toolchains. And in this toolchain, there's, for example, Wasm-opt, a tool that is very popular in the ecosystem. So Dart uses it for Flutter. We have Java, who use it with J2CL. We have Kotlin. As you've seen yesterday, there's Rust that use it with WasmPack. So it's a pretty popular tool out of many tools that you can find in Binarian. So new features coming to Binarian. I just want to list a couple of them. So both tools always follow the standards process really closely. So whatever is being proposed and developed in the standards process, you will typically see it reflected here. So support for multi-threaded Wasm garbage collection is a good example. Support for new proposals in general, as I just said, like imported strings, annotations, support for outlining, and so on. So there's a lot of things happening. We're also working on updating the exception handling in Binarian so that it is compatible with the old approach, but also implements the new one. And obviously, there's just constant maintenance work to make the code smaller, faster, better, and so on. Then there's Emscripten. In Emscripten, new features that we're working on are work on action ref, so that we get support there as well. There's work happening to get TypeScript support for the complete Emscripten module, so that it's a little easier for TypeScript developers and just JavaScript developers who use IDEs, for example, and also profit from types, even if they're not using a typed language, to just make programming and working with Emscripten-generated code easier. We're also working on ES6 modules for Emscripten, and we also have a project investigation where we look at type bindings for web APIs. And also here, a lot of work on reducing, improving the code. And we have some bundling explorations, and Thomas is going to dive a little deeper into that now.
Yeah, thanks, Tom. So in addition to all the Emscripten tooling and Binarian stuff that Tom just mentioned, a new area that we're just starting to look at is providing better support for the WebAssembly library ecosystem for web developers. Web developers are very used to bundler functionality like Webpack and Rollup working with their JavaScript, where it's able to take that JavaScript and do stuff like dead code elimination, code splitting, tooling to help keep their modules small. And in the scenario where a web developer is coming over and taking something off of NPM that's already been compiled to Wasm and wrapped in a JavaScript API, which is the common pattern, basically all of these tools break on WebAssembly. You have to ship the entire module, and that bloats bundle size, and it can be a real problem for Wasm adoption. And so we want to improve this situation, and we're hoping to work with some of these bundlers, but it's still extremely early days for us in this area. So in addition to all of that tooling that we build, we obviously also build the V8 engine itself. This is the engine that powers both WebAssembly and JavaScript in Chrome, other Chromium-based browsers, Node.js, and some other runtimes as well. It runs on a variety of different platforms and architectures and can be embedded either in any C++ application or just run in its own standalone mode. V8 has a few different compilation pipelines, and when we see a piece of WebAssembly, it starts its journey in what we call liftoff, which lazily compiles functions the first time they're hit to get really fast startup. WebAssembly is then further, for hot functions, optimized off the main thread in our optimizing compiler Turbofan, soon to be named TurboShaft. And then that optimized code is swapped in for ongoing execution and cached so that on subsequent runs, it can utilize the optimized code directly. We have some new features that we've relatively recently actually fully enabled and shipped in Chrome. One of these is multi-memory, which allows a WebAssembly module to have multiple memories in a single module. Tail calls for optimized tail calls by replacing a call with a jump. The relax SIMD set, which expands the set of SIMD operations to allow for better optimized code, but might have different outcomes on different architectures. And then last, but certainly not least, is the WasmGC support, which is in Origin trial, which is kind of like a beta program for APIs in Chrome. And this, of course, adds support for garbage-collected languages like Dart and Kotlin, which we've already talked about at this conference. Shipping in November. It already shipped. Yeah, in Origin trial, already shipped. Some other features that are testable behind a flag, if you want to check them out, is Memory 64, which allows you to do 64-bit memory indexing. The exception handling proposal to incorporate the latest updates while still supporting the old version. JSPI for allowing WebAssembly to interface with JavaScript's Promise integration system. And this really helps you better integrate and support sync and async code communication. And then lastly, string built-ins, which is a minimal and general mechanism for importing specific JavaScript primitives. And for example, this really helps speed up calling web APIs, which tend to be very string-based, and can really speed up those calls. And now Tom is going to talk about WasmGC.
Yay. So WebAssembly garbage collection. It's a feature where WebAssembly essentially allows you to manage the memory of objects. So in the end, this then allows us to port managed languages like PHP, like Dart, and so on, Kotlin, over to WebAssembly in a more efficient way. So classically, how this works is you have the source code, you have the language optimizations, and then typically all the optimizations in the Wasm MVP workflow happen before the WebAssembly generation. And then finally, you end up with Wasm MVP. The new workflow with WasmGC would be now you have the source code, you have the language optimizations, then you can create WebAssembly garbage collection, which is higher level, and then on top of that, you would run the optimization. So that's a little different, and allows you to get a couple of optimizations in that would not have been possible before. So classically, whatever language you come from, you end up with WasmGC, and then you have optimizations that you can, in a concrete case, do with, for example, Wasm opt that is part of binarian. This is not just ivory tower theory, this is actually used in practice. So Kevin's talk yesterday on Flutter went into this a bit. So we have Dart, it has common front-end, type flow analysis, representations, code generation, and then the final step would be optimization with binarian until you end up with the optimized WebAssembly code. So new WebAssembly garbage collection features that are coming or optimizations that are coming to binarian are listed here. So again, it's a lot. All are linked. We will share the slides so you can go into detail if you want. Just type pruning, or key virtualization, so you can turn indirect calls into direct ones and so on. So there's a lot of detail here, so we don't really have the time to dive into it. If you are interested, do so by clicking on the links afterwards. Else, just know that there's a lot of optimizations that are happening at this stage. And again, we do everything not in the ivory tower, but we actually look at how does it work in practice? Does it have an impact? So we looked at Java compiled to WasmGC. And you can see here, high risk better. So we ran a couple of benchmarks, Box, 2D, Delta Blue, Ray Trace, Richards. And you can see with Wasm optimizations, it's always faster. So that's good news. If you optimize, things get faster. That's good news, but it's kind of obvious. But you also want to make sure that what you assume to be true actually is true in practice. And now we have the next section of the talk, which dives into a number of Google products. And I hand over to Thomas again.
Thanks, Tom. So yeah, one of the first ever products that really tried to tackle WebAssembly for a large application was Google Earth. Google Earth, I think we've all tried it, looking up like our home address and stuff. It's a very fun tool and very useful. And it started its life as a C++ desktop app that you had to download, but it always had aspirations of being available directly in the browser. They were able to port their C++ application code to Android through the NDK and to iOS through Objective-C++. But the browser still eluded them. And early on, they tried to use native client, which of course eventually was sunset and transitioned into WebAssembly. And when the WebAssembly train came along, Google Earth very eagerly jumped onto it and was able to now be available in all the browsers. They were also able to benefit hugely from threading, which was something you really couldn't do previously effectively in JavaScript. And this, here you see how much faster it got in terms of FPS with the threaded version. And they were able to drop fewer frames, which we're actually going to look at directly here. You can see the threaded and non-threaded, how much faster it zooms in on the Empire State Building, and that it more smoothly pans around and gives a much more pleasant experience thanks to the multi-threading of WebAssembly. And now Tom is going to talk about Google Sheets.
Yeah, so Google Sheets, I guess you've all used it or seen it at some point. Again, reminder, this is one of the products where we have several applications, Android, iOS, and so on, iPadOS, and of course, the web where this application needs to run. So in Google Sheets, there's one central piece, which is the so-called calculation engine. We call it Calc Worker. And this runs in the server and on the client. The screenshot below actually shows the WebAssembly code of this running. So if you get lucky, we run an experiment where this is explorable in live production. So if you get lucky, you can hit the Wasm Calc Worker. It's written in Java that is then transpiled into Clojure JavaScript, traditionally, for the client with J2CL. This has some limitations, but it tends to work pretty well. And this was done in the past. And now we started an experiment where we took the same idea, the same Java calc worker, and compiled it to WebAssembly with WebAssembly garbage collection using J2-Wasm. And for large spreadsheets, the team actually saw a 1.8x speed improvement on large sheets. So it was not universally, but for large sheets where this really, really matters, the team saw quite a almost 2x impact speed improvement, which is of course pretty cool and demonstrates nicely that going Wasm is the faster option in many cases. This was, as I said in the beginning, a collaboration between the various teams at Google. So the V8 team, the standards team, the sheets team, the J2CL project team, and they worked on porting the Java code over to WasmGC, or compiling the Java code over to WasmGC. And in the beginning, they expected performance benefits, but they of course didn't know in the beginning would it work. So they ran frequent benchmarks with various optimizations. And it turns out that from the many optimizations that are listed on the slide a couple of slides before, speculative inlining was the one that gave the biggest speed impact. So you can see here various optimizations compared against each other. So you can see speculative inlining did really make a big difference here. And now the next product that we're going to talk about is Google Photos. Over to Thomas.
Yeah, so another product at Google that really benefits from WebAssembly, and I know one of my favorite products is Google Photos, who was able to use WebAssembly in specifically their photo editor. Google Photos wanted to use a single code base to target all of their platforms, iOS, Android, and web. And it's that old dream of write once, run everywhere, now finally realized with WebAssembly. And this allowed the photo editor to deploy to the web with full feature parity and allowed them to have all of their platforms maintain that feature parity as they make changes and improvements to the product itself. They use things like SIMD for filters, enhancements, and editing directly, which really speeds up some of these photo manipulation operations. And they also benefited from the increase from 2 GB to 4 GB of addressable memory space, which ended up halving their number of out-of-memory crashes. Now, this will also improve further once we get to the Memory 64 proposal, which allows for 64-bit indexing of memory. Now, I know some of you are probably thinking oh, great, Chrome is going to use even more memory. But in reality, this is short-term memory that you're using while you're editing a photo, and ultimately it's something that you would have had to boot up like a native application like Photoshop to do otherwise. Now Tom is going to talk about Google Meet.
Yeah, so Google Meet, you probably have seen it during the pandemic if you never tried it. But it's also, of course, something that powers a lot of businesses. Google Meet uses SIMD for echo cancellation on desktop, and I have this demo here that hopefully you will hear. We tested before, so let's see.
Can you hear me clearly? It's critical that we update the figures in section 11.7 by 9 AM tomorrow.
So you can see how big of an impact this makes, and I experience it a lot with dogs. So I have barking dogs right next to my house, and I always apologize for them being so loud because they really are loud. But then the other end would always be like, I didn't even hear anything. So there's a lot of noise cancellation, echo cancellation happening in Google Meet, and it's really, really good.
I have been in a lot of meetings with you, and I have no idea that there were dogs. So
they are. A new feature that you can also try on desktop is studio lighting. So that's a pretty cool feature. I really encourage you to play with it. You don't have to hop onto a call to test it. You can just do so locally. So you can see how the tester here is placing virtual studio lights on the screen, and then you can see how you can change the intensity of the lighting and so on. So really, really cool. Works in real time thanks to SIMD. We also use SIMD in Google Meet for background blurring, filters, and masks. So everyone's favorites, the stupid hats and the bunny ears and whatever. So all this works thanks to SIMD. It runs the same AI models on the desktop and on mobile. And on desktop, it uses MediaPipe. And MediaPipe is a library that has a Wasm pipeline that does the following steps. So for background blurring, you of course need to separate the background from the foreground. And for this, it uses a model called MobileNet v3 Small. And yeah, before this needed to run in real time. So before the model was really, really big. So they made it smaller. They reduced the size by 50%. And it turned out this didn't result in massive loss of quality. It was still good enough, precise enough. And it gave us a 2x speed improvement. So you can see the pipeline here. So you have the JavaScript side, which gives us the video texture as an input. Then we run ML inference on top of it. This gives us a low resolution mask. Then we have refinement that gives us a refined mask. And then finally, we have the rendering step that gives us the output texture. Depending on how powerful or not the device is, so if you have a small mobile device, of course, this is something different compared to a massive desktop computer. We can skip some of the steps. For example, not calculate the refined mask, and the results will still be pretty good in general. And this leads us over to the next section of our talk, which is libraries. And over to Thomas again.
Thanks, Tom. So yeah, in addition to some of these products at Google that use WebAssembly, there are, of course, also a large set of libraries. And Tom already covered one of these first ones, MediaPipe, which, as he talked about, is used in Google Meet. But it's also a general library that anyone could really use. And this does on-device machine learning for everyone and contains everything you need to customize and deploy to mobile, Android, iOS, web, desktop, edge devices, IoT. Does things like hair removal, which you might not think was too relevant for the two of us, but as you can see here, it even finds the tiniest shreds of hair and is able to segment those directly out, which is really useful, again, for video Meet applications.
And over to TensorFlow. So a lot of you may have heard the name at least. Some of you may have actually used it. TensorFlow, and specifically Tensorflow.js for running TensorFlow in the browser, does have, among others, a Wasm backend. And the reason is many devices still don't have a good enough GPU. And the CPU, this means the CPU remains important and relevant for the time being. And interestingly, it can actually outperform WebGL because there's a shader execution overhead when it comes to switching over to the GPU, to WebGL. And it uses SIMD and threads via xnnpack. And quick sidetrack for xnnpack, that's a library that is highly optimized for neural network inference operation. It works on ARM x86, WebAssembly, and RISC-V. It's not intended to be used directly, but it's intended to be embedded in more high-level libraries, like, for example, TensorFlow, TensorFlow Lite, PyTorch, ONNX, and so on, MediaPipe. And it does support Wasm MVP, Wasm SIMD, and also there's even experimental support for relaxed SIMD operation. So sidetrack xnnpack is being used in TensorFlow, MediaPipe, and so on that I just mentioned. And why am I talking about backend so much? Well, because counterintuitively, maybe, using the Wasm backend can sometimes be faster. So look at these charts. It compares different devices, Pixel 4, ThinkPad, MacBook Pro. And you can see, in this case, lower is better, so smaller is better. WebGL is the blue one, so it's a pretty solid baseline. Wasm pure is typically slower, or almost always slower. But then Wasm plus SIMD plus threads outperforms WebGL in all cases, which is counterintuitive maybe, but you can see depending on the task, it can really make a difference. So when people say go to GPU, careful, test with actual data, test with your actual task, if it's really worth it. A product that uses TensorFlow's Wasm backend directly in production is Adobe Photoshop. You can see here the image, or the object selection tool, and it's using TensorFlow directly to run this task, separating the object from the rest of the image. It's faster because it runs locally. It doesn't involve server cost, and the app can work offline. So a lot of advantages for a company like Adobe. And with that, over to Ink.
Thanks, Tom. Yeah, the last library that we want to cover is Google Ink. And this is a kind of freehand stylus input for doing vector graphics with extremely low latency, which was extremely critical for when you're kind of like drawing You really want that cursor to like follow you directly and draw those vectors. And one of my favorite things about the Ink team when we talked to them was that they said without WebAssembly, it just simply wouldn't have been feasible for them to support the web at all. They said they had like dozens, if not hundreds, of engineering years built into this tool, and the idea of rewriting in JavaScript, even if they could get the performance in JavaScript, just simply wouldn't have been feasible for them to even support the web. I think that really highlights some of the values of and benefits of WebAssembly's portability. Ink is used in a bunch of different Google products. Canvas, which is the built-in drawing for Chromebooks. Google Classroom uses Ink for annotating PDFs. Google Keep for drawing little sketches and notes. I know I use this myself a lot. Google Photos for annotating photos that you can do. And then YouTube also for annotating and drawing on your stories.
Yeah, so over to Skia, and specifically CanvasKit, which is the WebAssembly version of Skia. So Skia is an open source 2D graphics library that provides a lot of common APIs that work across various hardware and software platforms. It serves as the graphics engine for Google Chrome and Chrome OS. We use it in Android, use it in Flutter, so I'm pointing at Kevin here. He showed you this in his talk yesterday. The Kotlin folks, I'm not sure if Salim is here. Yes, I can see Salim's hand. So Kotlin uses it in Compose Multiplatform. It's also used in many other products. And it offers a WebAssembly build for easy deployment of its graphics APIs on the web. And it's powerful, fast graphics without having to write WebGL code, which is a huge advantage, I can tell you, as someone who has tried and given up on learning WebGL. Right, so quick review from what we saw yesterday. So shout out here to Salim's talk for the details. Kotlin compiled to WasmGC uses Skia CanvasKit to draw UI pixel perfect on various devices. You can see here different devices ranging from desktop to mobile to, that's it, desktop and mobile, running in a browser and running native in, I think this is a macOS native application here, in the background. And they use a wrapper called Skiko for pixel perfect rendering in Kotlin, Compose Multiplatform. Again, what we saw yesterday, if you use Flutter, watch out for a file called skWasm, or skwasm, as I learned yesterday from Kevin how they say it. They use the Dart Skia bridge to, in C++, compiled to skwasm in their product so that you can run and get pixel perfection also in Flutter applications. Shameless plug for my colleagues Kevin's talk, but here is the demo screenshot, so really try it, it's impressive. It is, as you can see here, a lot of UI components that you typically would need, radio buttons in general, tabs, color pickers, and so on. So it's pretty impressive how far you can get with this. So shameless plug to check out Kevin's talk. And with this, some closing thoughts. So Google really, really loves JavaScript. It's important for us because we're a big company, but still writing once and running anywhere makes a difference. It allows us to share business logic across different platforms, and we bet heavily on Wasm, as we have shown today. Visibly, so we could show you a bunch of things, but also hidden behind the curtains, some private things that we would love to talk about, but it's unfortunately just not something that we can share publicly. We started early betting on Wasm, and Britney Spears' voice here, we still believe. So it's still something that we heavily believe in. We continue working on it. And with that, thank you very much. If you want to get the slides, it's goo.gle/WasmIO2024. We're the two Thomases. We're both easily findable on the interwebs. So if you don't want to ask your question here, you can do so offline via email, Twitter, Mastodon, whatever. And with that, thank you very much.
Yeah. And I think we've almost used up our time, but happy to take a question or two, certainly. You can, again, always find us out in the hallway as well. OK, then thank you so much, everyone. See you around.
Thank you.